This is section 2.5, further applications of right triangles. And the biggest brunt of this is going to come from what we call bearing. So that's going to be the first thing we deal with. All right, give me a chance to kind of talk you through this and make this make sense to you. There are two methods for expressing bearing. Now, if I say, hang on, I need to get my bearings, what do I mean?
Coordinates. Where you are.
My coordinates, where I am, or maybe would it be like where I am in relation to something else? Does that make sense? Okay. So when we talk about bearing, we are dealing with direction. We are not necessarily talking about a triangle. Okay, that's not like we're not inside a triangle, but we're also not talking about the XY plane. We're dealing more with a map. And when we deal with maps, we don't talk about X coordinates and Y coordinates. What do we talk about?
Longitude, latitude.
We do. We talk about longitude and latitude. And what are they measured in?
North and south.
North and south. How many degrees north? How many degrees south? How many degrees east? How many degrees west? So when you're dealing with something out in the real world, such as airplane travel or ship travel and things like that, and one object in relation to another, you are typically talking about bearing. And unfortunately, it is measured completely differently than rotation in the XY axis system. When a single angle is given, such as 164 degrees, it is understood that the bearing is measured in a clockwise direction from due north. This is the first method of measuring bearing. So if I say something has a bearing of 32 degrees, like I have in this first example here, that means that I'm standing here, or the object in question, and if we stand and look due north, and then rotate 32 degrees clockwise, not counterclockwise, clockwise. If I rotate 32 degrees clockwise this way, this vector here is where the object I'm looking at should be located. I don't know where along the vector. I would have to have some other information to figure that out. But if I am here, and I look due north and rotate clockwise 32 degrees, and then so imagine like turning your body and looking along this vector. Somewhere out there is the object in question, and that object has a bearing of 32 degrees. That's the first. So let's just look at some different rotations. Let's look at 164 degrees. If I say I have a bearing of, something has a bearing of 164 degrees, you start from the point in question, you look due north, and then you imagine rotating 164 degrees. And you don't have to break out a protractor. We're going to draw these sketches, but you do want them to be realistic. So sometimes I will make east-west marks as well. So I'll kind of make the whole little thing there so I can see it, all right? And then I say, all right, if I go this much from here to here, I would be at about 90. If I went all the way to here, I would be at
180.
So I say 164 is pretty close to 180. So we just drew it right here. So there is the vector that tells you a bearing of 164 degrees. Notice that the bearing is trapped between the due north and the stopping vector, your terminal vector there. When we talk about it on an XY axis, we talk about it as a ray, but when we talk about it in the real world, we talk about it as a vector. Okay. All right, 229 degrees of rotation. So if that's my bearing, this would be due north. This would be due what? This would be due, and this would be due south. Okay, so 90 degrees would get me to due east. 180 degrees would get me here. If I went all the way to 270, I would be here. So 229 lives about right here. So this angle from here around to here is said to be a bearing of 229. And anything on a bearing of 229 from this mark right here would have to lie along that vector. and finally one that's over 270. If we want to talk about a bearing of 304 degrees, you have to have your point of reference. That's sort of your origin. That's where you start from, okay? And it changes for each object. So we start here, we look due north, and then we start to measure. About to here would be 90. This would be 180. This would be, and so, you know, all the way around would be 360. So 304 is about right here. So that measure. So that means all the way around would give me 304 degrees. How much would be inside right here? If this is 304 degrees, how much is this? 56, right? Yeah. So sometimes with bearing, you know, you may want to go back and you may want to redraw it differently so that your angle is smaller. So you could label the 304 or the 56. But the idea is to get a crucial sketch because they're really important in solving these problems. Okay, so let's do an example of a word problem that would require you to use that first type of bearing. This problem says there are radar stations A and B, and they're located on an east-west line. They are 3.7 kilometers apart. Station A detects a plane at point C, and the plane is on a bearing of 61 degrees from Station A. Station B simultaneously detects the same plane on a bearing of 331 degrees. We would like to find the distance from A to C. Now here's the thing about your book. The one they give you first, you're going to usually list first. So if they say A to B is east-west, A is still going to be west of B. I wish they had said west-east because it confused people. But if you get it drawn backwards, you'll know because of where it lands. Like, they won't meet up, is what I mean. So I'll show you in a second. But we are going to put Station A towards the west. Yeah. So this we're going to call A. And then we're going to say 3.7 kilometers apart. And then we're going to put Station B. So you have to label it. It's really important.
Is that what you're saying? Like it doesn't make sense that it's east-west when it's...
Once I put the bearings on, you'll see. Okay. Let's start from Station A. The plane is on a bearing of what from there? 61 degrees. So if I go due north, which I'm not very good at today, and I rotate from due north, so you start from due north and you rotate 61 degrees. That would be about right, I don't know, here? Would that be about 61 degrees? Ish of rotation if I go from here to about right there? Okay, now we're going to draw the vector. Now here's the thing. I don't know where point C is. It's going to be very hard to figure out unless I know something else. I wasn't told how far to go. So point C technically, well, I'm not a very good drawer. Let me try that again. Point C technically could be anywhere along this vector, right? So maybe it's between point A and B, but maybe point C, or that plane, maybe it's over here, further east even of this. We won't know until we map the bearing from the other one. But which of these two angles is 61? And here's the kicker. The top one, right? The one from due north. That is 61 degrees. That doesn't mean I can't find this one. I can. But right now, that's all I know. Okay, now from point B, I have to go a bearing of what? 331. So if I start point B from due north, okay, and I rotate from due north 331 degrees. So this would be 90, this would be 180, this would be 270. So 331 is about there. And then I draw a vector there. Do you see where the two vectors hit? What is right there? C. What is C? That's the airplane. So that airplane is right there. So now I know it takes two different points of reference to get there, but now I know where that airplane is. It's between them, about right there. Then I go through and I label that bearing. So all the way from here around to here was 331 degrees. Got it? Okay, that's all I know. And from that, I want to find the distance from A to C. So this is what I'm hoping to find, the distance from A to C. You could also call that little b. So let me see if I can talk you through this, and then if you have any questions, we will take them, as many as you need, okay? All right, first off, because right now we're studying right triangles, I really hope that's a right triangle, because we don't get the ability to study non-right triangles until we hit chapter 7. So between now and chapter 7, if it's a triangle problem, you better hope that it's a right triangle. So if I had to guess, which of those 3 points would you guess is the right triangle, the right angle? I would bet C, yeah. But we can figure it out by just doing a little like intuitive math here, or deductive maybe. All right, if this is 61 degrees and that's north and this is east, together this whole angle has to be 90. So these two have to be complementary, which means this has to be 29 degrees. So now I actually know an angle inside the triangle. All right, if from here all the way around to here is 331, how far is it to just right here?
270.
Okay, so what's 331 minus 270? 61, which I think is kind of interesting that this angle turns out to be 61 degrees. So you will have to use your 90-degree marks, your little tick marks, your 90, 180, 270, 360, to find the missing angles that are inside the triangle. And if these two together, 61 and 29, make, that means this must be 90. And now I know that that's a right triangle. And I can use it to either solve it with Pythagorean theorem, which I can't do because I only know one side, or I could use a SOHCAHTOA equation to figure out that missing x. There are two ways we could do this. I could start from the 29. If I start from 29 here, and I'm trying to find x, that would be adjacent over hypotenuse. See, this is my hypotenuse if I start in this problem. If I start from here, this is my adjacent. So that would mean that cosine of 29 degrees must equal adjacent over hypotenuse. And then I could just set that up as a proportion, cross multiply, and I could find the value of x. So it looks like x has to equal 3.7 times the cosine of 29 degrees. So let's pause right there and let's calculate x. Okay, so that gave me 3.236092916 kilometers. And if I look at my significant digits in the original problem, it has only how many? So it looks like 3.2 kilometers. Now I would expect that to be less than 3.7 before I even work the problem, because 3.7 is my hypotenuse and it has to be the longest. So like if I had gotten 5.2 as an answer, then I would have said, something's wrong, because your hypotenuse always has to be the longest, right? Yeah. Okay. All right, that's one way to work this problem. What if someone said, I don't want to use the 29, I want to use the 61? If we decided to use the 61 instead of the 29, what SOHCAHTOA equation would that be?
Opposite over adjacent.
Let's see, that would be opposite over hypotenuse, yeah. So that would be sine, yeah. That would be the SOH. So the sine of 61 is equal to x over 3.7. But then when you solve it, you would get the same thing. And it would still be 3.2 kilometers. So it really shouldn't matter. Okay, any questions we need to address right this second on that? That's the first example. We went through it very slowly, and all of your bearing problems that give a single angle are going to be done that way. Now you need to watch out for this. Bearing is not always stated in the problem. The words bearing and direction are synonymous. If the problem says in a direction of 331 degrees, that is the same as saying on a bearing. So a problem doesn't have to say bearing for it to mean bearing. It will either say something about north, south, east, west, or it will say the word direction, or it will say bearing. If you're unsure if it's a bearing problem, always ask me.